Welcome back to Arts Learning. In this video, we'll be going over work and power, which precedes the types of energy we learned, and what we're going to learn after this is the conservation of energy equation. Okay, so this is a very important tie-in topic, which you need to have a strong grasp on. These terms, work and power, are generalized, right? Work is just, you go to the office and you work. But in physics, work has a different concept and a different meaning, okay? Work is force along the motion of an object. FD cosine theta. So, if there was an object, so actually let me remove these axes. If you pushed like this on a ramp object, okay, and the object went this way, that means you did work, okay? If the object is going in the way in which you're doing work, in which your force is acting, you did work. The equation for work is FD cosine theta, okay? The cosine theta just gets the, so you can assume that if this is F and this is the distance, right? Which is a very common scenario. There could be a sled here. I could be pulling the force like this, right, with the rope, but the sled moves horizontally. So then how am I going to measure how much it moved? Well, that's just going to be the force times the cosine of theta, right, which is this adjacent side. That's what's going to give me how much it moved in the direction of this component, how much it moved in the direction, okay, that it's moving, how much force is acting on the direction it's moving. So FD cosine theta. So if you drag it longer, that means you did a lot more work, because that makes sense, right? If you drag it longer, you're exerting more energy and more energy. So if D is larger, work will be larger. If F is larger, which means you're exerting a greater force, similarly, energy is also going to be larger. And this cosine theta is the perpendicular component. The perpendicular component, if you had a perpendicular component here, that would completely be irrelevant, okay? So for example, force sine theta is neglected, right? It's only the cosine theta here. We only want the work, or we only want the force that acts in the direction the object is moving. If I can pull in 1,000 different ways, right? But the block still goes horizontally. I want the force in the component which pulls the block in the horizontal or vertical direction, okay? And in this case, this is the horizontal direction. So it doesn't always need to be horizontal. You might look at cosine theta and you might be like, oh, horizontal. No, right? If this is my force, this is my distance, it would just be the cosine theta angle here, okay? So I can get my horizontal component of my force, and I can find out how much that force is acting on this distance. And similarly, if you had a force that was straight up and a distance that was to the right, you can understand how you'd have zero work, right? Because you're pulling upwards, but the block is going this way. So obviously you're not doing any work, right? You're not pushing it in the direction of motion. And also cosine of 90 degrees would just be 0, right? And then imagine if you pushed it one way, right? But the block actually went the other way, which is pretty rare in, reality, right? That probably doesn't happen a whole lot. But if it does, that means the block is doing negative work, okay? Because cosine of 180, which is the degrees between the direction you're pushing, right? That's -1. All right? So work is just how much did it move in the direction you're pushing it in. But the cosine, okay, the component that aligns with the distance, which component aligns with the distance and how far does it go. And something you might notice is that FD, so work is also measured in joules, right? The same unit as energy. Work is in a way energy, right? Because if you move a block, you're exerting energy, and that block is gaining energy. So work is in a way energy, but it's more applicable. So for example, this energy, me pulling this block, what would you call it? You wouldn't be able to call it much, right? I mean, the block has kinetic energy, but what's the energy I'm acting on it? That's work non-conservative, okay? I'm pushing the block, or I'm pulling it. And if I wanted to find out the energy there, it'd be FD cosine theta, okay? So that's how you find out energies that are not given by formulas. You use the work equation. So very similar. I'm not going to say the exact same because we do have the cosine here, right? So it only depends on the angle, how far does it move in the direction you're pushing it in. How far does the force component take you in the same direction? And power is the rate of change of work. It's either how fast the work goes, right? How fast do you do the work is done, or how slow it's done. So you can see that here, right? Watt over time. Work over time. I was getting a bit ahead of myself there. So work measured in joules, time measured in seconds. We know a joule is a kilogram meter squared per second squared. And if you divide that by a second, you're going to get a second cubed in the denominator. Right? And this unit is what we called a watt, in honor of James Watt, a physicist who contributed a lot to power. So whenever you hear a 50-watt light bulb, or it's usually very common in light bulbs, but it's definitely everywhere else, right? Like in your toasters or any appliances, this is what it means. How fast does the work happen? And you wouldn't think that, right? Because in reality, power means something different. It's just how strong you are, how much presence you have, right? But here, it means the rate of change of work. So if you do a large amount of work, right? But if you do it in a large amount of time, then that's not really a large amount of power, right? Because if you do it in a large amount of time, that means the denominator is larger, which means it's going to nibble away at your power. But if you did a large amount of work in a small amount of time, then you're going to get your maximum power, because the smaller the denominator is and the larger the numerator is, the more power you have, right? Similarly, if you did a small amount of work in a large amount of time, that's the worst combo you could have, right? Decreases your power by a lot. The numerator isn't high and the denominator is so high it's literally destroying your numerator. So yeah, power doesn't depend on just watt or just work or just time. It depends on both of them. So let's try a tad bit tricky problem, okay? A 1200 watt motor lifts a 50 kg crate. Okay, so the crate is like this, and it's moved up. And we need to find the speed of this crate. So the 1200 watt motor is over here. 1200 watts is equal to work over time, right? And we know that, what's the work we're doing here? We're pulling this block up. What's the force we're exerting? Same direction, right? The distance of the block is upward, and the force we're exerting is also upward. So cosine, here, the angle between these two, is just 0 degrees, right? And cosine of 0 is just 1. So when I do work is equal to FD cosine theta, F here is just the force of gravity, because that's what I'm opposing, right? and then I'm actually bringing it up a distance. That's why it doesn't accelerate as fast, right? It goes up at a constant velocity. Because I don't have a net force. It's the same force, but I'm still moving it up a distance. So the force of gravity here would be 50 times 9.8 times d, which is, we don't know, right? But we know that's 490 Newton here. And the velocity is going to be the power over the force. So that's going to be 1200 divided by 490, or 2.45. Now this equation might seem a bit random, right? But think about where it comes from. Power is kilogram meter squared per second cubed. And when you divide that by force, which is kilogram meter per second squared, your units are going to be meter per second. So velocity is equal to power divided by force. Okay, if you didn't know that already, here you have it. Alright, so let's try some practice problems. As always, the more comprehensive problems will be on artslearning.com. But for right now, let's just walk through it, right? And then once we get to conservation of energy, it's going to get a lot trickier. Okay, I'm assuming you gave it a try. A 20 Newton force pushes a box 5 meters along its motion. Find the work done. So a 20 Newton force, this kind of force, pushes a block 5 meters like this. So the force is aligned with its motion, right? Along its motion. So that means what is the angle between them? 0 degrees, right? They're both aligned. So the work is just going to be equal to 20 newtons, which is a force, right? Force times d, which is 5 meters, times cosine of 0. Cosine of 0 is 1, right? So 1 times 5 meters times 20 newtons. So this is just 100 joules. Okay, so now let's try the next one. A 50 Newton force pulls a sled 8 meters at 60 degrees above horizontal. So the sled is being pulled 8 meters in the horizontal, but the force is 50 newtons at 60 degrees above the horizontal. And we need to find the work done. So the work is just going to be F, which is 50 newtons, times D, 8 meters, times the cosine of the angle between them. In this case, 60. We know cosine of 60 is 1/2, right? And we know, so 1/2 times 8 meters, we can just write that as 4 times 50 becomes 200 joules. There you go. Okay. A motor does 6,000 joules of work in 4 seconds. Find its power output. Well, this is pretty simple, right? Power is just work over time. So if you're already given the work, which is 6,000, and we're already given the time, so 6,000 joules over 4 seconds, then it's pretty simple, right? You just divide 6,000 by 4, which is going to give you 1,500 watts. Now, a 300 watt motor pulls a cart at a steady 2 meters per second. Okay, so 300 watt motor is pulling the cart at that pace. Find the pulling force. So 300 watt, right, is the power. And what equation did I show you? Velocity is equal to power over force, right? So 2 meters per second is equal to power, 300 watt, divided by a pulling force, which should be 150 newtons, right? I mean, if you didn't understand where I jumped there, that's just 2 is equal to 300 watts over 2 meters per second here. over H, and then 2H is equal to 300 watts, and H is equal to 300. So watts divided by meter per second is just newtons. And there you have it. That's your work and power practice set. As always, it's not that hard, right? I'll go over the harder problems later. Now, we're going to be going over the master equation in the next video, okay? The equation of conservation of energy. And that's going to be the trickier one. So stay tuned for that, and give me a like and subscribe if you enjoy my content and you want me to reach other people as well.